Hello and welcome. You're tuning in right now for Improving the Design of Optical Devices through Stop Analyses. This webinar is presented by COMSOL and hosted by Photonics Media. And I'm Sarah Weiler, I'm the webinar coordinator at Photonics Media. You'll be hearing today from several voices from both COMSOL and Altasim Technologies. First, from Altasim Technologies, we'll hear from its president and co-founder, Dr. Kyle Copenhaver, who has an educational background in civil engineering and prior to Altasim worked for the Department of Defense and the Edison Welding Institute. Next, you'll hear from Joshua Thomas, senior engineer at Altasim, who has a background in mechanical engineering and for the past 6 years at Altasim has provided consulting and training support in COMSOL multiphysics. From COMSOL, you'll hear from Christopher Boucher, who is a lead developer at COMSOL with a background in aerospace engineering and physics. Our presenters today will be focusing on the development of STOP solutions for optical devices. If you have any technical problems during the webinar, please try logging out and logging back in to fix it. But if that doesn't work, please don't worry. This is being recorded and it will be online in a couple of days. As well, if you would like a copy of today's slides, there's a PDF available for download right in your webinar dashboard. You can get that at any time. But if you would prefer that we email it to you, we can do that. Just reach out at webinar@photonics.com. And finally, there's going to be a Q&A at the end of today's talk, but you can ask a question or leave a comment for us at any time in the chat on your screen, and we will respond to you either today or later by email. So that's all from me. I'd like to introduce our presenters, Chris Boucher, Dr. Kyle Copenhaver, and Josh Thomas. Welcome.
Excellent. Thank you so much, Sarah. All right, so by focusing on the story that we're going to tell today of Altasim's experience in developing simulations that enable our clients to save time and money while optimizing the performance of their optical devices, what you're going to learn is you're going to learn the why and how of STOP simulations and how they are useful in developing optical designs. So today's webinar is about Altasim sharing our experience with STOP analyses. And in the future, we're going to offer you an opportunity to share with us about your interest in STOP analyses. A couple of my colleagues, Lynn Smith and Mike Kopp, will reach out to you and see if you're interested in sharing with us about your experience. So speaking of sharing experiences, the first thing we'd like to do is go to a poll question so we understand a little bit better about what your knowledge is in this area.
Absolutely. I'm going to launch this poll. So everybody, the question is, how much experience do you have with using STOP simulations? The possible answers are, this webinar is the first I've seen of it, or I have seen it but never used it. My company has used it, but I have not. I have used STOP with tools other than COMSOL multiphysics, or I have used COMSOL multiphysics for STOP simulation. I'm going to give you a couple more seconds to respond. All right, thank you. I'm going to close the poll and share those results. Question again, how much experience do you have with using STOP simulations? And 39% of you said this webinar is the first I've seen of it. 33% said I have seen it but never used it. 6% said my company has used it but I have not. 17% said I have used STOP with tools other than COMSOL multiphysics, and 5% said I have used COMSOL multiphysics for STOP simulations. Thank you very much, everybody.
Awesome. Thanks, Sarah. Thanks for going through that. And you can see there's an awful lot of people who are fairly new to STOP analysis. So one of the things I want to make sure of is that we address things from a fairly basic standpoint. So I'll make sure we tailor our comments to that. So first, let's take a look at the roadmap of what we're going to talk about today. So we're going to start with the definition of a STOP analysis. Then we're going to go through some of the challenges associated with designing optical systems that are subjected to mechanical and thermal loads. And then I'm going to share with you an overview of both a traditional and then a multiphysics STOP analysis. Then after that, what I'm going to do, I'm going to turn the demo, the presentation over to Josh Thomas, my colleague, and he's going to share a demo with you. And then, we'll talk a little bit more about COMSOL. And then we'll go to Q&A. So let's go ahead and get everybody on the same page about stop analyses. So a stop analysis is a combination of three important physics. The analysis consists of a structural component to assess the deformation, a thermal component to calculate temperatures, and finally the optical performance to assess how the system performs. And ultimately, the final outcome of these analyses is the optical performance, so it really is the most important design feature. So the structural analysis assesses how the mechanical and thermal loads deform the system. The thermal analysis calculates the temperatures within the system, and then this temperature data could be provided for the thermal loads in the structural analysis, and then also to the optical analysis for temperature-dependent material properties. And then the optical analysis then combines all that information for the structural deformation and the temperatures to calculate what the optical performance of the deformed system looks like. So stop analysis is applied to optical systems, things like cameras, telescopes, spectrometers, lasers, those types of things. Typically, when we see stop analyses, there's something unique about the environment. There's something where the mechanical and or the thermal loads of the system are going to produce a deformation. And space is an excellent example. It's an extreme environment. The thermal loads can be significant. And even the mechanical loads can be important. You think about how tight the tolerances are for space-based optics, and then also the realization that you got to minimize weight, which is going to produce lower stiffness structures generally, which can end up producing larger displacements. Simulations have become a primary tool for optics engineers. So engineers and scientists that are designing optics, they use numerical simulation, they optimize with numerical simulation, and they'll even troubleshoot their designs using simulation. So being able to extend optical simulations to include the effects of thermal and mechanical loading is going to help designers reduce their product development cycle and the cost. So it's going to drive down the time and the cost. So our experience shows that the largest payoff of implementing simulations are for designs with complex physics, and stop structures definitely fall into that category. Engineering calculations just generally don't provide sufficient accuracy for designing the systems. So what are some of the challenges associated with stop analysis? Well, let's walk through some of these. Let's talk about structures. Right, mechanical loads produce structural deformation. So load on an end of a beam is going to cause that loaded beam to deform. And simulations are used regularly to solve these types of problems, right? The thing is that you can take those deformations from this kind of structural analysis and include those in the optical systems. So let's talk a little bit about how the structure heats. So right, when a structure heats, it's going to expand. Whether we think of that as a change in length, a change in area, or a change in volume, a temperature increase is going to produce a structural increase, and then conversely, a temperature decrease is going to reduce the structure size. These thermal deformations need to be included in the stop analysis. Now, other thermal challenges for stop analyses are the effect of the temperatures on the optical properties. Now, optical properties of materials often vary with temperature and also wavelength, as you see here. So any stop analysis may need to include the effects of temperature change on those material properties. Now, the last set of challenges that I want to mention are really more in the category of numerical challenges. I've mentioned the challenges associated with the physics in a stop analysis, but when you do a simulation, there are challenges associated with the simulation. Structural and thermal simulations typically use a numerical method called the finite element method. And the software uses that to solve the equations of the physics, of the thermal and the structural physics. Now, optical performance typically uses ray tracing methods. So to conduct a stop analysis, you're going to need to combine those two different numerical methods. Now, traditionally, these methods were combined by using different pieces of software. And so the thermal analysis would be done in one software, and you collect the temperature data, pass it off to the structural analysis. Now, this data handoff could be time-consuming and error-prone. Fortunately, for this handoff, the thermal and structural analyses are typically both done using finite element analysis, and that data handoff is generally pretty straightforward. There were times in the past when it wasn't, but it's gotten fairly straightforward. The biggest challenge in a traditional stop analysis is handing off the structural and thermal data to the optical analysis. Traditionally, this really has been quite time-consuming and can produce significant errors. So in a multi-physics stop analysis, the process is simplified. By using a unified simulation environment, the thermal and the structural and the optical can all be done seamlessly. This reduces the frustration of time-consuming data transfers and increases the confidence in your results by reducing the errors. So in a few minutes, my colleague Josh Thomas is going to demonstrate the development of a stop simulation. And this is going to be a simplified version of some of our consulting work that we did for a client. We're going to demonstrate the development of a stop simulation that is a simplified version of our consulting work for a client. What Josh is going to do is he's going to walk you through the model development process and show examples of results. And I'd like to provide an overview of the demo before we get into the details. Okay, so the overall engineering challenge is to determine the optical performance of a telescope that's being heated by the sun. And the sun's going to generate a local heating based on the orientation of the telescope. Now, the demo is going to walk you through the 5 major steps of the simulations. These 5 steps are geometry and materials, physics and boundary conditions, meshing, solving, and post-processing. The physics will include heat transfer by conduction, convection, and radiation. And then there'll also be structural mechanics and geometrical optics. To orient you on the geometry of the telescope, let's first take a look at what we're actually going to simulate. And what this is it's a titanium housing that contains 3 lenses. And so you can see the geometry here that Josh is going to be working with. The 3 physics are going to be heat transfer, structural mechanics, and optics. Now let's look at the heat transfer first. We're going to include conduction, convection, and radiation as heat transfer mechanisms. The radiation is going to include surface-to-surface radiation of all the surfaces in the telescope. And Josh is going to set up opacity-controlled radiation and use a surface emissivity of 0.8. The heat source will be the sun as an external radiation source, and we're going to locate it at an infinite distance so that the rays are then moving purely in the negative z direction. The heat flux is going to be 1,500 watts per meter squared, and that's going to be the heat coming from the sun. So looking at the structural mechanics, so this, first of all, we're going to use all linear elastic materials, so no plasticity in this. And then we are going to fix the constraint boundary conditions here at this band that you see highlighted. And we're going to fix that so that all 3 displacements are set to 0. So this is a fixed condition through here. We're also going to be using geometric optics for the problem. Now, generally, as I mentioned, material properties are going to be dependent on temperature, but in this case, we're going to assume that the refractive index is temperature independent. But we are going to include the wavelength dependence on the refractive index. Now, COMSOL includes multiple ray release patterns, and we're going to use a hexapolar pattern because we have a circular cross-section of our optics, and we want the rays to illuminate the lenses uniformly. To graphically represent the workflow, let's look at the thermal, structural, and optical physics. The blue arrows represent the coupling between the physics. And all the physics are going to be sequentially coupled in this. So the thermal is going to couple to the structural, but the structural is not going to affect the thermal. And as I mentioned previously, we're not using temperature-dependent material properties. If we were, there would be a link between the thermal and the optical. For cases where the optics actually produce heat, there would then be a bidirectional coupling between the thermal and the optical. And again, that's not included in the demo that we're doing today. Now, with the physics set up, we can move on to meshing, and Josh is going to walk you through that, and then we're going to move on to solving the problem. So the thermal and structural mechanics are both going to be solved in a stationary format. So what that means is that the thermal steady state, the structural mechanics is quasi-static, but then we're going to solve the transient problem for the ray optics, or the ray tracing. And so then what we've got is we're going to be coupling together a stationary solution and a time-dependent solution. And then once the problem is solved, we can post-process the output. So the simulation provides a really rich set of data. Each physics is going to provide outputs, and then we can understand how the three physics interact by looking at those outputs. So let's look at an output from each physics. So the sun's shining on the top of the telescope here, and that produces a local hotspot. It gets up to about 88 degrees C. The temperature gradient produces a complex displacement in the structure, and this displacement that you see here is going to alter the optics. The deformed geometry is going to produce ray trajectories that the simulation engineer can then use to assess the performance. And then these results are going to show the effect of thermally induced deformation on the optics. On the left-hand side, you see the simulation without the deformation. And on the right-hand side, you see the results with the deformation included. This information is going to enable the designer to locate the focal plane, including the deformation effects. The designer is also going to be able to visualize the actual spot diagram and make changes to the optics to make that spot geometry look more like the spot on the left. For those of us with less than perfect eyesight, I think about this diagram as showing the astigmatism of the system. So at this point, I'd like to turn the presentation over to my colleague, Josh Thomas.
All right, thanks, Kyle. So I'm going to now build the model that Kyle just described. And this is the COMSOL interface, and you should be seeing that now. And I'm going to walk through this over the next 15, 20 minutes or so. The first step is to go through the model wizard, where we pick the space dimension. We're going to assume 3-dimensional. And then we're going to add in the 3 different physics phenomena. The first one will be heat transfer with surface-to-surface radiation. And we're also going to add the solid mechanics physics. See, the different physics interfaces are being collected down here. And then finally, we'll add in the ray trajectory, ray optics physics under the optics branch here, geometrical optics. Okay, so once you've added in the physics that you're interested in including in your model, you click the study button here. And we're gonna, to start out, we'll just assume a stationary study type, but as Kyle mentioned, we're going to be adjusting that as a stationary, time-dependent sequential setup. So we'll take care of that here in a little bit. All right, so now we have the main modeling environment that we're going to be working in. The model builder section over here on the left. And the first thing typically that we're doing is defining the geometry. And so we're going to import that from file. So I'm going to right-click geometry, select import. And I'm going to browse to my desktop. And this is a CAD geometry of the telescope. You could also use the COMSOL native geometry building features to build this from scratch as well. I'm going to hide a few of the boundaries here so you can see inside. Okay. And we can rotate this in 3D and see we have the convex lens here on the front, the convex lens on the other side here, where you can see the convex side here, and then the convex side here on this third lens. Okay, so we're going to set up the material properties now. And I'll do that using the materials feature. We're going to add from library first the titanium housing. Under the built-in section, I'm going to add in titanium here. Add to component 1. Okay. So now we have, now COMSOL has decided now all material regions are titanium. We're going to need to specify the lens, 2 different lens types for the lenses. And so I'll reintroduce this material window. And under the optical section here, we have some material specifications specific to the optical problem and different types of lenses here. So the first one we'll add is the optical glass shot, and then different type here. We're going to add in this NBK7. All right. And then we'll apply that to the front end lens and the back end lens. Now, one thing you'll see is that we have the dispersion coefficient array here, and then we also have the refractive index coming in from the database. Now, you'll see that we don't have the thermal or mechanical properties for these, so we'll need to enter those in by hand. You can also put these in as parameters if you wanted to vary these and do a sensitivity study on the thermal conductivity or other properties here. Heat capacity. So there's your thermal properties that we just entered, and now the structural properties for the Young's modulus and the Poisson's ratio to specify the stiffness of that lens. Okay, so then we'll also want to specify the lens properties for this center lens here. We'll go back to the material browser, and this lens will make this an O'Hara lens, and we'll specify this particular type here, LAH84, and select that lens. All right, and then we'll need to do the same thing for the thermal properties. And the Poisson's ratio. All right, so that specifies our material properties. Now we're going to set up the boundary conditions for the heat transfer physics. The default thermal insulation is not quite what we want to do. We want to override that with both convective heat flux and surface to surface radiation coming from the sun. And so we'll do that now. We'll put a heat flux boundary condition and add this to not all of the boundaries. We only want the exterior boundary. So I'm going to use this feature called an explicit selection. So we'll say all domains, but then the output of that selection will just be the exterior boundaries. Okay, so this will be exterior boundaries, and now we'll be able to use this defined selection anywhere in the modeling workflow, not just on the heat flux. Okay, so we'll use that here, and we'll give a convective heat flux value of 5 watts per meter squared Kelvin to an exterior temperature, ambient temperature of 20 C, room temperature here. So we would assume this would be a telescope at experiencing convective heat flux, not like maybe close to like a natural convection. COMSOL does also provide more precise natural convection lookup tables for external or internal natural convection, also forced convection that you can specify here. But for today's demo, we'll just give a value of 5 watts per meter squared Kelvin. All right, we can also set up the surface to surface radiation. And to do that, we'll use our selection for just the exterior boundaries. And then on the diffuse surface settings, we'll need to specify the emissivity, the default opacity controlled. Will give us the correct radiation direction for the surface radiation. And we'll set a value of 0.8 for the emissivity of all surfaces. All right, so now we're going to apply the sun source. We'll use a external radiation source. Kyle mentioned that we want to place this in the positive z direction at infinity. So we will use our infinite distance source position, and then we'll give a incident radiation direction of vector of 0, 0, -1. So that will be in the negative z direction. So from the top down will be the sun source. And then we'll give it a flux value of 1500 watts per meter squared. Okay, so there's our sun heat source. All right, so now our thermal model is completely defined. We could solve this for the temperature solution if we wanted to, a typical model workflow, probably you'd want to do that after all that work just to make sure everything was working well. But for demonstration purposes, we'll just go on and start to set up the structural analysis as well as the geometrical optics analysis too. So for the structural analysis, we'll need to add in the thermal expansion coupling. So if you right click on multi-physics, there's a thermal expansion feature, and we'll add this to all domains. You can see the equation here. So this is thermal strains are going to come from the coefficient of thermal expansion times the local temperature at any point in the system minus the zero strain reference temperature. So any temperature above ambient is going to cause an expansion, and we'll start to be able to get the distortion measurement based on this coupling term, where the temperature solver is going to feed those temperatures to the structural analysis. We do need to constrain the structural analysis to get rid of the rigid body translation and rotation so that this will solve. And to do that, we'll right-click on solve mechanics and add that fixed constraint along this ring that Kyle mentioned. Okay, so we're constraining the displacement to 0 here. Now, if this were not mounted to additional structure with a full constraint there, you could also use what's called a rigid motion suppression. So if this were just a device sitting on a table that was heating up and wasn't constrained and it was free to expand in all directions, you could use this rigid motion suppression to give the minimum amount of constraint so you're not introducing any additional external constraint stresses. So COMSOL does provide that for you as well. All right. We do need to give the material properties for the coefficient of thermal expansion. So since we added in this coupling, we've got this new value that we'll need to add in for each of the lenses. The titanium already has the coefficient of thermal expansion as part of the database here, but we'll add these in for the Schott and O'Hara lenses. All right, so 7.1 E minus 6, and then O'Hara will be 6.1 E minus 06. All right, so we are now just about ready to set up the geometrical optics. So these are the two physics that are going to feed in to the geometrical optics analysis. Those are all set. But what we'll need to do, one setting that we found to be particularly important in the simulation work that we've done at AltaSim is that the geometric shape function is very important to increase the resolution here. We found that the discretization error was a bit high for the default setting here of automatic. So if you're ever doing these analyses, we recommend switching the shape discretization on the finite element elements to be cubic Lagrange. And so this is going to increase the resolution from the default isoparametric, which is a quadratic geometric shape function to be able to have a better, higher fidelity resolution to the shape of these lenses by switching this to cubic Lagrange. So that's an important setting, kind of under the hood, but you do have access to it here. And then when we're actually solving the ray tracing, there's a number of settings that we'll go through now. And so for geometrical optics, we'll assume that this is air. So we use the Ayer-Edlin model for the optical dispersion model. We'll also need to, the lenses, we're going to specify an anti-reflective coating. And so that's going to do that, you'll need to first also check this compute intensity and power. And then we'll also add in this added computation for visualization of the optical path length during post-processing. We'll need to, on the medium properties, we'll change the default here to get the dispersion model from the material. This is that wavelength dependent refractive index that Kyle referenced and is built into the Schott and O'Hara lens material definition. So we'll get that wavelength dependent refractive index here. We can also adjust the reference vacuum wavelength here, depending on the application that you're working with. And then we're also going to set up the anti-reflective coating on all the lenses so you don't get any rays bouncing back. Okay, so we'll do that with the material discontinuity. And this is going to be on all of the lenses. So you would add in the surfaces of the lenses one by one like this. And then under the setting here for thin dielectric films, we'll specify the anti-reflective coating. All right. And then you can also set up the release from grid. Kyle mentioned the hexapolar settings that you would set up here. And for the sake of time, I'm not going to adjust those settings, but you can define the spatial orientation of the hexapolar grid and the direction of the vectors. So we're going to specify those running in the positive X direction so that they're coming in through the telescope. As far as finite element meshing, COMSOL will allow you to build a physics-controlled mesh. We don't recommend using the default physics-controlled mesh for this particular physics. We recommend switching to a user-controlled mesh and then adjusting the element size just on the lenses to be extremely fine. So I'm going to set that up now. So this is the default physics controlled mesh. We can see the mesh is relatively coarse along the lens surfaces. It's real important for these types of analyses to represent the shape of these lenses more accurately. And so we refine the mesh on the lenses with an extremely fine mesh setting. And then that cubic discretization that I showed before allows the shape of each one of these triangular faces to vary cubically. And so we're really going to be able to capture the fine levels of distortion that are going to come about due to the thermal signature and the heating from the sun. Okay, as far as solving goes, the default COMSOL assumes you want to solve all physics in all modeling steps, but that's not the case for this sequentially coupled analysis. Is not exactly what we want to do. So first we solve heat transfer solutions. So we uncheck these, and then we can set up the solver to then solve secondly for the structural analysis. And then we add a ray tracing step as a time-dependent analysis for the third step. And then COMSOL will solve each of these sequentially. So again, step one, thermal solution, feed that information to the structural analysis, solve for that in step two, and then step three, we solve for the ray tracing based on the deformed shape. Now, the big setting of maximum importance here is this include geometric nonlinearity here. So by checking this box, you're going to include the effect of the change in the shape of the lens, which is maximally important for this particular application. This model takes about 7 minutes to solve. So instead of clicking compute here, I'm going to go ahead and open up a completed version of this and just spend a minute or so showing you some of the plots that you can do. So this one is computed. All right, so now you get some of these post-processing plots that Kyle mentioned before. We've seen some of these images. This is the temperature distribution in the telescope hot spot at the top where the sun is shining down up near 360 Kelvin. That's about 88 Celsius. You can look at the surface radiosity too to see the flux coming from the sun up above. And then that's going to produce deformation. So I'm going to do a quick slice plot of the structural deformation. And we'll go in units of microns. Okay, so now our slices are in the YZ plane. We'll go ahead and align these along the ZX plane and set the value to 1. And so if you look at this from the side here, you can see the back lens here has relatively low displacement due to the constraint near this band. This lens is displaced, maybe 15, 20 microns, but then at the front, you can see large amount of displacement through this lens up over 50 microns. And there's a preference towards the top, right? So we'd expect some amount of distortion here for the optical simulation. And so when we look at the results for the ray tracing, you can see coming from the left, we set up the hexapolar grid here coming from the left. And so the rays are moving from left to right. They're focused in through this lens and then through the second lens here for the focal point in the back. Here we're visualizing the color is the intensity, but we could also look at the optical path length. Remember, we set that based on to come up with that calculation for us. So here's optical path length plotted over those ray trajectories. And we could also set up a spot diagram using a 2D plot group. Under more plots, you have a spot diagram here. And under the focal plane, we can create a focal plane that gives us the spots through that focal plane. And you can see the distortion here that showed in one of those images. So this region here is the upward direction. You can adjust the focal plane orientation settings to make it look like the plot that Kyle showed. But you can also add in a color expression for the radial position. Might make this a little bit more informative to an analyst. All right, so we can see how the lens's distortion pattern is collecting these the spot diagram over to the right here. So this would be upward in the towards the sun direction where you have that added deformation. So with that was a quick demonstration of how you build a model like this from scratch. So I'm going to pass this back over to Kyle.
Awesome. Great job, Josh. It's a lot to juggle and giving a demo. You did an awesome job. So one question you might be asking is, why is Altasim Technologies involved in this ComSol-sponsored webinar? The answer to that question is because 17 years ago, Altasim and ComSol started the ComSol Certified Consulting Program. We did that to provide high-quality consulting for multiphysics problem solving. So Altasim is a separate company from ComSol, but we've partnered to help serve the multiphysics marketplace through our consulting, our training, and our sim app development. Now, the model that Josh showed you is a simplified example of our consulting services. And what we do is we plug into the existing engineering capabilities of a company and provide a rapid, high-quality virtual prototype team of people that are experienced in using the software because we use it 40 hours a week, every week. So in addition to consulting, Altasim is the only company other than ComSol that provides a full suite of training classes, from introductory to a wide range of physics and advanced classes. And we do this to help our customers move up the learning curve for themselves and be as independent from Altasim as they choose to be. Now, the third major area where we solve the multiphysics analysis space is in this apps section. And what these are, and Christopher is going to talk a little bit about this. This is an opportunity for engineers to be able to run simulations of their specific problems without learning how to use ComSol in detail and without requiring the expense of a full ComSol license. So with that, I'd like to close out our section of the presentation and turn it over to Christopher.
Okay, yeah, thank you, Kyle and Josh, for that great presentation. I just wanted to follow up with a couple of general comments about the ComSol software, sort of stepping back and looking at it from a wider perspective. So what we've seen today is a combination of three distinct physical phenomena going into a single computational model: thermal analysis, structural analysis, and optical simulation. Of course, the ComSol software actually goes even beyond that. Here we see the software product suite, and we have dozens of different add-on modules for different physics areas. So it's not just structural, thermal, and optical, but also if you want to include fluid flow, for example, or you want to extend your structural model to include nonlinear materials, if you want to include chemical reactions, if you want to for example, if you have a much smaller scale geometry, you might choose to do your optical simulation using a wave optics or RF-based approach instead of a ray tracing approach. So for almost any physical phenomenon that's governed by differential equations, we have a software solution for that. We also interface with an enormous variety of different file formats, and here you can see just a smattering of the different formats that we support. There are a number of so-called live link packages that allow you to simultaneously interface with one CAD package for changing your geometry and also run ComSol to solve equations on that geometry in real time. Another great benefit of working with the ComSol software is that you can see all of the equations that are being solved are exposed to the user. So at the very top level, you can choose which type of physical phenomenon to model, such as structural or thermal, but then you can also see what are the actual equations being solved at an extremely low level. You can view and even modify these equations. And you also have very fine control over the type of numerical method used to solve those equations. Most of the time it's the finite element method, FEM, but we've also seen ray tracing today, and the ComSol software encompasses other numerical methods as well, such as the boundary element method, large eddy simulation, and much more. Now, one thing that you might run into when working with the ComSol software is just, well, there's the sheer overwhelming number of different options that you can have. Pretty much you right click anywhere in the software and you're probably going to get a menu with dozens of different options for different types of boundary conditions that you can apply, or source terms, or plots, or study steps. The whole thing can get pretty overwhelming. So we also provide a ComSol application builder that lets you turn any ComSol model into a user interface. And then you can distribute these applications, which you can think of as the underlying model with a custom user interface. You can easily share that with people who might not have the time to work with the software and all of the options that it provides. You could either distribute these within one organization using either ComSol or a product called the ComSol server that lets you run apps. And we also offer a dedicated ComSol compiler. So you can actually take a model turn it into a simplified user interface, and you can compile that into a standalone executable, which can be shared with anybody, even with people who do not have a license for COMSOL. So you could create and distribute your models in a variety of different ways. So here we see just one screenshot of what an app could look like. So instead of those dozens upon dozens of different options that we saw earlier, you can restrict the user to only changing certain inputs. You can restrict them to only choosing certain materials or certain boundary conditions. You can restrict the range of any input. And you can also configure buttons to automatically run certain combinations of studies or to display certain combinations of plots. So apps allow a certain level of customization even beyond what working with the COMSOL interface supports. With the COMSOL server, you can administer what applications are accessible to people in your organization, and you can either run it on a dedicated COMSOL client or in a web browser. Alternatively, if you use the COMSOL compiler, you can freely distribute these to just about anybody that you want to, even people who are not COMSOL users. So in essence, what we try to do with the COMSOL software is we try to make it either as easy to use or as flexible as you need it to be for the task that you have in front of you. So if you are an experienced user, you're going to find a wealth of options for just about anything you might want to do. If you want to share your results with people who might be new to COMSOL or not be experienced in simulation, you can create an app that streamlines their work and restricts what they can change about the engineering design, and just about anything in between. So with that, I would like to turn this back over to Sarah, and we're ready to start our Q&A session.
Thank you very much, all of you. Yeah, everybody in the audience, we are going to spend the next couple of minutes taking questions, but I just want to remind you, if we don't get to it today, or if you think of another one, don't worry, we can get back to you by email. So I've got a couple to start with. In the demo example, option calculate optical path was activated. Is there any tool available to visualize optical path difference?
Yeah, I can take that. And actually, Sarah, if you want to allow me to share my screen again, I could show, probably just take a minute or
Sure.
less to show that. So we're looking at the COMSOL application again here. So we, that's right, we did look at the optical path length here, but you can do optical path difference as well. It would require using this Poincaré map, which is a 2D plot group type, which is available here. And then you can add a color expression to that, and then you need to define a cut plane. So there's a process to go through where you have to add an additional release point, and the rays that are coming in from the front need to plot that relative to an additional ray source. So it takes a little bit more to do, but you can plot the optical path difference as well if you need to, if you're interested in that metric.
All right, thank you. Also in the demo example, telescope tube, the telescope tube was modeled using solid elements. Can it be modeled using shell elements in combination with solid elements?
Yes, so you can, we added those solid elements here, but if you go to add physics, you can see that COMSOL has the full range of different element types available, and you could do layered shells if there was like some type of composite buildup or solid mechanics shell, layered shell membrane, etc. So that's available, and you're able to interface that with the optical analysis as well.
How would you include temperature-dependent material properties in the ray tracing analysis?
I can take that one again too. All these are related to the demo. That's cool. So temperature-dependent properties. The really nice thing about COMSOL is anywhere there's an edit field, you can just essentially, anywhere there's an edit field, type in an expression, right? So for example, we looked at the shot material for this lens, and these have room temperature values, but if you just, for example, for the thermal conductivity, you could multiply it by capital T. Capital T is your temperature field, and that's spatially dependent. And you could do that for the these other lens properties as well.
All right, thank you. This next question is for Chris. When do you think COMSOL will fully integrate wave and ray optics modules together with thermal and structural analysis to reach a true multi-scale, multi-physics design platform for optics and photonics? Big question.
All right. So first off, a little bit of background information. So the ray optics approach to performing optical simulation is it's only appropriate to do ray optics when you have a geometry that is much, much larger than the wavelength of the radiation. So we might be looking at lenses that are on the order of centimeters in diameter, but we're dealing with visible light that's on the order of hundreds of nanometers. So it's many orders of magnitude larger. Now, the place where you might want to perform a wave optic simulation is when you have a wavelength that is comparable to the geometry size. So both have a certain region of applicability to them. Now, as far as coupling these two and performing a true multi-scale simulation, we took some steps toward this in recent versions where we allowed the output of a wave optic simulation to be used to release rays. One example of this is that in the current version of COMSOL, you can solve a wavelength scale model using the wave optics module or RF module. You can perform what's called a far field transformation. So you can get the distribution of electric field amplitude at a very long distance from that object. And you can actually use this to release rays, and the amplitude and polarization of the rays will be based on their initial directions. So we've taken some steps toward multi-scale modeling, going from the small scale to the large scale. The thing that we don't have yet is the opposite coupling, where you take the rays and use them to excite a wave. So we've sort of half done the setup of multi-scale electromagnetic simulations, and eventually we want to get there the rest of the way. So we have some, so I guess we have some limited capability, and we're going to get the rest of the way eventually.
All right, thank you. Do the rays always go in straight lines through each object? Could you perform ray tracing in graded index media? That is for whomever would like to take it.
Christopher, do you want to take that?
Yeah, sure, I can take this. So the answer is yes, you can perform ray tracing in a graded index medium. And there are a few different ways that you might see a graded index medium. One is if you have a temperature-dependent refractive index and the temperature follows a distribution, then the refractive index will also follow a distribution. So there are two different ways that refractive index changes, right? It changes abruptly where one material meets another, and in that case, the ray will reflect and or refract, or the refractive index could change gradually, as in you have a refractive index that's a function of a non-uniform temperature. Another example might be you might have a varying chemical concentration of a species, and that might affect the refractive index. And yes, if you trace rays through that sort of domain, you will actually see the rays curve. So as long as you make the refractive index change continuously, then you can see rays follow curved paths.
All right, another question for any one of you. Does the structural analysis just include thermal stress, or can it include other applied forces like gravity?
Yeah, I can take this one. So yeah, the structural analysis includes both the mechanical and the thermal loads. So you can include a body force like a gravity, or an external force like an applied force, that sort of thing. In addition to the thermal loads, or the thermomechanical loads.
All right, thank you. I'm going to take a couple more questions, but don't worry if we don't get to it. I'm seeing a bunch. We will follow up. In the demo, how did you set that stationary solver 2 is fed with stationary solver 1 results and transient solver with solver 2?
Yeah, so that is set up. I mean, I showed that. I guess COMSOL will automatically, when you have multiple steps, it will use the results from the previous step intelligently. So it will know that it needs to read in any values of variables that you're not solving for in the current step. It'll use those values from the previous step. So as long as you do a multi-step setup, COMSOL will read in those variables for you automatically. And so those couplings, with the combination of the multi-physics couplings that you, as long as you set those up properly, you know, the temperature dependence on the optical properties, and you make sure to check geometric nonlinearity so that the optics will see the deformations. Then the way that I set the solver up, it's really as simple as just having those multi-step set up there and then clicking compute.
Which physics modules come with the basic COMSOL license, and which physics modules are add-ons that require a separate license to be purchased?
Okay,
That's a question for Chris.
Yeah, I can take this one. So the word module actually means an add-on product. So pretty much all of the modules are purchased in addition to the basic COMSOL package. Now, in terms of what physics modeling capability you get, if you buy the COMSOL multiphysics software, then you generally get some fundamental physics in many different areas. So for example, you get electrostatics, you get conductive heat transfer in solids. For fluid flow, you will get laminar flow with a somewhat restricted set of boundary conditions. You can get magnetic fields, but only in 2 dimensions and just the out-of-plane field. So a lot of the broadest physics areas, you'll get the fundamental physics there. And then as you purchase different add-on modules, you will both get access to new physics interfaces, but you will also extend the existing capability of some of the interfaces that you already have. So for example, if you want to model heat transfer with surface-to-surface radiation, then you would get the COMSOL multiphysics software with the heat transfer module. Now, ray optics is entirely in the add-on, so the ray optics doesn't, there's no capability for that in the base package. The other thing that you do get with the base package is you get a set of generic differential equation interfaces. So you always have the option to define your own equations. It's just that the built-in equations, you get a bigger variety of those as you purchase more add-on modules.
All right, I'm going to ask you one more question, Chris, and then I'm going to wrap up the Q&A. Can you calculate wavefront error using COMSOL multiphysics?
Okay, so Joshua demonstrated a couple of different result plots during his demo, and the only one that I could add to that is there is a dedicated plot type that if you've already identified your focal plane, then you can compute the Zernike coefficients that fit to the optical path difference of rays passing through that plane. So you can, if you're computing optical path length, then you can extract the Zernike coefficients for things like coma and astigmatism and spherical aberration. And you can either plot these, so you can plot the different aberration terms, or you can extract the numeric values of these coefficients.
All right, thank you all of you for presenting and for taking all of those questions. I am seeing many more, and so as I said, if you think of another one or if you're awaiting a reply, feel free to email us or look out for an email from us later. And as well, if you would like a PDF of today's slides, you can download that right from your webinar dashboard now, or you can email us at webinar@photonics.com to get a copy. That's webinar@photonics.com. And again, this session was recorded. It will be online within a couple of days, and you won't have to search for it. You'll get links to it in your email inbox as well. So thank you, everybody, for being here. Thank you one more time to our presenters, Chris Boucher, lead developer at COMSOL, Dr. Kyle Copenhaver, president of Altasim Technologies, and Josh Thomas, Senior Engineer at Altasim Technologies. And thank you everybody here for participating in improving the design of optical devices through stop analyses. This is presented by ComSol Inc. and hosted by Photonics Media. Goodbye, everybody.